Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. My name is Siti Nasina binti Johari. Today, I would like to present to you our research entitled Real-Time IMC-PID Control and Monitoring of Essential Oil Extraction Process using IoT. So, we are from Faculty of Electrical Engineering, ITM Shah Alam, Selangor. So, let's begin the presentation. So this is the outline of the presentation. First, we will go through background of studies. Second, literature reviews. And third, methodology. Fourth, result of and discussion. And lastly is the conclusion. So for the background of studies, we know that steam distillation essential oil extraction process, SDEOE, is the most common technique used for essential oil extraction. Steam is produced by boiling out water inside the extraction tank. The extraction process requires a long time to run, a very long time to run. An operator is needed to monitor the steam temperature regularly. So the process is required approximately 1 to 2 hours. Therefore, we need a mechanism that allows continuous monitoring without any human presence need to be in that site. So remote monitoring and control of steam temperature of SDEOE system using Internet of Things IoT. The monitoring system was enhanced by enable output monitoring by display on a handphone in real time using Blynk application. So basically, when we install the Blynk application, we can monitor the extraction of essential oil process, monitor the temperature, whether it's a good, whether the temperature within the range of temperature that we want. Because if the temperature is too low, the extraction of extraction oil, the process of extracting the oil is not produced. And if the temperature is too high, the molecules of the essential oil is broken or damaged. And that's why we always need to monitor the temperature during the extraction process. Furthermore, we also we also have internal model control, ESP8266 which incorporated into the system. So the problem statement, as I mentioned before, this essential oil extraction process requires a very long time to run, approximately to 1 to 2 hours, and need a presence of human at that site to monitor the temperature regularly. So this operator, she or he cannot do anything beside monitoring the temperature of during the extraction process. So this operator could not leave the laboratory until the extraction process is finished. So she cannot go to have a lunch, or want to go to the toilet, so she cannot leave the laboratory. So the research objective is, first, we want to control and monitor the steam temperature during SDEOE. Second, we want to enable the steam temperature monitoring by display it and control it using handphone with IoT as a platform. So, okay, next is the literature review. So let me explain briefly about the internal model control. Internal model control was developed by Manfred, which there are two parts in the designing IMC. First is the internal model itself, which is to help to focus the process response by adjusting the manipulated variable. If you can see in the figure 1, the internal model itself is the one that have the process model G prime PS below. So that is the internal model. Next part is the filter, which the filter need to be reached the desired robustness in the controller design. Therefore, there are two parts designing IMC. So you can see the derivation of to have the PID controller parameters. You can see in details in the technical paper how the derivation we have until the derivation conducted until we have the PID controller parameters. So the filter is the lambda that if you can see in the equation KC, so we have lambda there. Lambda is the filter of the IMC tuning method. And the recommended value for the lambda is more than 0.8 theta because of the model uncertainty due to the pattern approximation. So next is the methodology. Methodology, we have three parts. First is the real-time control diagram. Second, hardware development. Third is the software development. So this is the real-time control diagram. So you can see in figure 2, that's the steam distillation plant that we have in our laboratory. And figure 3 is the schematic diagram of the steam distillation plant. Okay. From this plant, we have the process model given in equation 3, where we obtain from the previous research. So, okay, when the value of lambda is higher, the response speed and robustness of the system is higher too. Table 1 indicates the value of lambda of 2 theta that being used in this project. So from the PID control parameter previously, we calculate by using lambda equal to 2 theta, and the parameters, the value of the PID control parameters are given in table 1. Next is the hardware development. So this is more to the IoT part. So the input is the temperature sensor that installed at the plant, and the controller is the NodeMCU Wi-Fi module, and output is our smartphone. The Blynk app, the Blynk app inside our smartphone. So next is the software development. Figure 5 is the Blynk application interface. So where the user can directly monitor the real-time data of the temperature inside the steam distillation tank, which display inside the Blynk application. So to program the NodeMCU, we are using IDE, and the coding is the C++ programming code. So for result and discussion, so you can see in figure 7 is the Blynk interface. Currently, we conducted the temperature, the experiment. Sorry, we conducted the experiment, and is quite successful experiment. So this is the real-time data that we have. The temperature during that time is 33 degrees Celsius. And the live signal process, so you can see in the figure 8, from 8:49 a.m. until approximately 9:50 a.m., 1 hour, okay, we can see the temperature is rising to our desired temperature. So the experimental is the desired temperature that we want is at 85 degrees Celsius. So we can monitor the temperature using our phone. Okay, in PID control, okay, we know that the overshoot was usually caused by an over operational gain or an integral wind up by the integrator. Therefore, we applying error switching to the controller. This switch only passed through the error when the error output value was 5 degrees Celsius lower than the set point. Because during simulation, okay, we have the not perfect result, but the the simulation result is not same as during the experimental, the real-time result, because because it's simulation. During real time, there are so many disturbance happen, like surrounding them. For this experiment, the disturbance is going to be the surrounding temperature, and the flow of the water inside the tank also can be the disturbance and will affect the result that we want. That's why we have this error switching installed together to make sure that the set point and the temperature that we want um, equivalent to the desired temperature that we already set it up. So this is the purpose of the error switching. So you can see the output of PID with error switching is quite same as the one that we have in our phone in the Blynk application in figure 8. So as conclusion, this study proposed a mechanism that control and monitor of steam temperature using IoT as a platform. The temperature inside the steam distillation tank can be monitored outside of the laboratory, which means that we don't need to monitor always the temperature inside the laboratory. So, what is the advantages that we can have is, first, overwarming of the distillation tank can be avoided. That's one of the advantages. Second, the operator can do anything besides monitoring the temperature during extraction process. And we can say that this mechanism can help them and to save their time. So next, we also have the error switching algorithm. So it can help to eliminate the integral windup. And IMC-PID controller gives the best result of the temperature control by maintaining the temperature at desired temperature, which means it does not have error. So that's ended my presentation today. I hope I hope this MCO will be ended so we can have a proper conference. Okay, that's all for me. Thank you so much. See you. Bye.